Hello, this is test 1 from this year, question 3. This question is a little puzzle to figure out two separate nuclear reactions. You're told that aluminum is bombarded with alpha particles and produces neutrons and positrons. Then when you stop bombarding it, the neutrons stop, but the positrons keep being emitted. So you figured out that it's actually, you're producing phosphorus 30, which then goes on to decay via positron emission. So you want to write out two nuclear reactions for this process. We know we have phosphorus 30 and the atomic number is 15. For aluminum, we know that this is 13. You can pretty much fill in the rest. So if we start with this one, because we don't know the isotope of aluminum that they're actually talking about in this case, but we do know that this phosphorus 30 decays by a positron emission. So it's going to be our second one. So I'll write it down here. Have the phosphorus 30 decaying by positron emission. You want to know what it's creating. So you're going to have a 14 on the bottom and a 30 on top. And that happens to be silicon. So now let's move one up here. You know you have aluminum, 13. Actually, you could have done this one first as well. Either way is fine. You know you're producing a neutron and you're producing phosphorus 30. So you can easily solve for what isotope of aluminum we're talking about. The number has to be 27 because on top we need to have a total of 31. So there's the two reactions. And yeah, you could have done them in either order, really. Doesn't matter. So that was part A. Now, part B, you have another similar little puzzle to go by. And this is about the nuclear bombardment of uranium-238 to produce the first synthetic element, which was uranium-239. And then that undergoes beta decay to give neptunium. So it's actually not even a bit of a puzzle. We're just writing down the two balanced equations here. So our uranium-238, you have to find the elemental number, atomic number. You're bombarding it with neutrons. You're generating uranium-239. And sure, we get some gamma kicked out of there. Now, uranium-239 is now decaying by a beta decay to produce neptunium. So you have a 239 on top, and we have a 93 on the bottom. So that's it for that question. And yeah, of course, you have neutrinos or antineutrinos and gammas and all of these, but that's okay for this case. Now, part C, get a little bit more math here. So in part C, we're talking about phosphorus 32, and you are given the fact that you have a particular mass in this case? No, we don't have a mass. You're given the half-life of phosphorus 32, which is equal to 14.3 days. In part A, you want to find the decay constant, K, in the units of seconds to the -1. So you need to transform your days into seconds. You can easily do that. You end up with 1.24 times 10 to the 6th seconds. For your equation that relates half-life and K, remember this is a first order process, all nuclear decays. K equals ln 2 over T1/2. So when you sum everything in here, you're going to end up with 5.61 times 10 to the -7 seconds to the -1. This was part I. Part 2, in this case here, you're given the fact that you have a 1 milligram sample, and we want to know how many disintegrations per second. That's the activity. Disintegrations per second. So how many atoms per second? So if you remember your equation for activity, it's just the decay constant times n. That's how many disintegrations per second. So we just need to find n in this case here. How many we're starting with here. You're told you have 1 milligram sample. So let's find n, which is the number of atoms. We have 0.001 grams. I switched to grams from milligrams because we have grams per mole on the bottom here. Times, or divided by 32 grams per mole. That's going to give me a value in moles. And to get rid of moles and get down to atoms, I'm going to multiply by Avogadro's number, 6.022 times 10 to the 23. That's atoms per mole. So you're going to end up with 1.88 times 10 to the 19 atoms. So when you sub that into our equation up there for activity, you're going to have an activity of 1.06 times 10 to the 13 atoms per second. Now the last part of this one, the third one, let's erase this for now. Find my marker. So in this part here, approximately what mass of our phosphorus 32 will remain in the original 1 milligram sample after 57 days? So A naught, the amount we started with, our time is 57 days. Remember your equation, this is first order, so we can find out how much is left based on this equation right here. So A naught is 1 milligram. You don't necessarily have to go into concentrations at all because well, milligrams, you can use concentration, you work out to get concentration, everything's going to cancel itself anyway. So you can go mass to mass. You can say how much mass is remaining to your starting mass. That's perfectly fine as well. But what you do need to do is switch your time into seconds because your K is in seconds. So that value there is 4.93 times 10 to the 6 seconds. When you sub everything in, your final mass you have left should be 0.063 milligrams.